Greetings, dear colleagues. In this video presentation, we want to introduce the telescopic need electrodes that reduce painfulness and labor intensity and increase the accuracy of tests in need electromyography. Need electromyography has a significant role in diagnostics of neuromuscular diseases. The drawback of this research is that it is painful, lengthy, traumatic procedure for the patient and a difficult and laborious one for the doctor. Routine electromyography takes about from half to 1 hour, during which the electromyographer constantly moves the need electrode to and fro in the muscle in order to obtain optimal location against the motor unit fibers. As a result, the procedure causes persistent pain to the patient and is labor-intensive for the physician. This is particularly true for single-fiber electromyography. This test requires proficiency of the electromyographer, that is, manipulating with the electrodes within tenths of millimeters, and collaboration from the patient. Even an electromyographer highly experienced in this methodology needs from 1 to several hours to conduct the test. A new type of mono and bipolar need electrodes has been developed by us in Telavi State University, Georgia, Caucasus. A telescopic electrode acknowledged as an invention by the state. It represents a hollow needle 1, see figure 1, with the lengthwise groove 2, in which the dielectric rod 5 is movably located with the 1 or 2 microelectrodes 6 and 7 are fixed on it. Microelectrodes 6 and 7 are connected with insulated electrical conductors vias 8, which are located inside the dielectric rod 5. Conducting vias 8 emerge from the upper end of the dielectric rod 5 and connect with the vias 9. A handle 10 is attached to the top of the dielectric rod 5. During the test, the hollow needle is immobile inside the muscle. Only the dielectric rod is moved, thus sharply reducing the painfulness of the process. Measuring of motor unit territory is used in electromyography. This parameter is important for both diagnostic of neuromuscular diseases as well as evaluation of the functional state of neuromuscular system. The motor unit of a muscle is a set of single muscle fibers innervated by the terminal branch of the axon of one motor neuron, and is characterized by a certain area occupied by it on the cross-section of the muscle. All muscle fibers that make up one motor unit are discharged simultaneously. Muscle fibers belonging to different motor units are discharged asynchronously. Eric Stolberg et al. Had elaborated macro-EMG and scanning EMG methods, which also are used to measure motor unit sizes in modern electromyography. When applying macro-EMG method, the size of the motor unit may be identified indirectly according to the amplitude of the motor unit action potentials. This method is rather labor-consuming and inaccurate as evaluation is made indirectly. Scanning EMG method is based on scanning, that is step-by-step, slow, gradual movement of standard concentric needle electrode inside the muscle within the distribution zone of muscle fibers of the tested motor unit, collection of data on changes in actual potential of the certain motor unit, and development of relevant image on the display. Additionally, a single fiber EMG need electrode used as a trigger is inserted in the muscle in order to register their action potentials from an individual muscle fiber of the muscle. and to identify the motor unit axial potentials being recorded by concentric needle electrode and belonging to the same motor unit from which axial potentials are recorded with the needle electrode for registration of axial potential from an individual fiber. This method allows precise measurement of motor unit territories. However, painfulness and traumaticity derived from the necessity of slow and gradual insertion of the electrode in the muscle is very high. These methods, macro EMG and scanning EMG, are applied and advanced in modern electromyography. To measure the territory of muscle motor units, we use the needle electrode presented above, which is characterized by the fact that a less 3 with a scale 4 is attached to the hollow needle. See figure 2. A cogwheel 10 is attached to the top of the dielectric rod 5. The cogwheel 10 fixes the dielectric rod relative to the less 3 and at the same time plays the role of a hand. Operating principle of the proposed electrode is based on methods of scanning EMG, gradual withdrawal of the needle electrode from the muscle and recording synchronous axial potentials of motor units provided by A. Stolberg and L. Anthony. Let's consider description of the operating principle of the proposed telescope needle electrodes and new methods for measuring motor unit territories of muscles. Before using the electrode, the dielectric rod 5 is placed in the hollow needle cannula vine. Then the needle electrode 1 is inserted in the muscle and the dielectric rod 5 is gradually withdrawn from the hollow needle while the hollow needle remains motionless in the muscle. While gradually removing the dielectric rod 5, if the microelectrodes 6 and 7 are located within one motor unit, the electrical activity recorded by them will be synchronous. When the upper microelectrode 7 cross the motor unit border and microelectrode 6 and 7 happen to be on the opposite sides of the border, that is in different motor units, the electrical activity recorded by them will be asynchronous. The depth of the motor unit's border L1 is identified according to the position of the cogwheel 10 as per the scale 4 given on the less 3. When the lower microelectrode 6 also crosses the border between the motor units and both electrodes are once again found within the border of a single motor unit, the electric activity recorded by them again becomes synchronous. Gradual removal of dielectric rod 5 from the hollow needle 1 continues with the hollow needle remaining motionless and the desynchronization points of the motor unit axial potentials are identified as motor unit borders in the muscle. L1, L2, L3, etc. Then the motor unit territories L2 minus L1, L3 minus L2, etc. are identified along the whole depth of the needle electrode. In order to identify the motor units and the areas of their crossing, we may employ two proposed electrodes in monopolar design. See figure 3. Using alternately dielectric rods of monopolar needle electrode together with the microelectrodes are moved from one motor unit to another, identifying desynchronization points as motor unit borders, depths, L1, L2, L3, etc., and identifying the motor unit sizes, L2 minus L1, L3 minus L2, etc., as well as the size of the areas of their crossing. They also offers a new parameter, motor unit density, which equals to the ratio of the number K of motor units on a certain segment L of a muscle towards the L segment legs in centimeters. To reduce the complexity of electromyography of single muscle fibers, we propose to connect a hollow needle and dielectric rod to a microscrew. See figure 4. On the dielectric rod 3 thread is created and the knot 7 is put on the rod. Scales 8 and 9 are applied to the moving mechanism case 6 and on the nut 7. When the nut 7 is fully turned, the mark on the rod, it is not shown on the figure, moves on one scale division on the scale 8. That is, the divisions on the nut 7 scale 9 are subdivisions of the scale 8 on the case 6. On the dielectric rod are affixed 1 or 2 microelectrodes. The proposed needle electrode significantly facilitates testing electric activity of single muscle fibers during electromyography, measuring jitter and fiber density. It also shortens the testing time as examination with the given needle electrode does not require high training levels of the electromyographer, since even a beginner electromyographer can easily move the dielectric rod for not only tens but also hundreds and thousands parts of millimeters within the help of the moving mechanism 6 and the micro screw 7. A micro screw may be connected to a micro electromotor and be equipped with the relevant software, which further reduce the labor intensity of single fiber electromyography. Despite the fact that it is believed that muscle fibers of the same motor unit are discharged at the same time, there is still a small asynchrony between their discharge, much less than the asynchrony between discharge of muscle fibers belonging to different motor units, which can be measured by modern equipment. It has been revealed that while recording action potentials of two adjacent muscle fibers belonging to a same motor unit, intervals in their discharge are inconsistent and fluctuate around the average meaning defined for the given pair. The variation in the latency dependent on the inconsistency in synaptic latency period is called jitter. Normally it is from 10 to 70 microseconds and being the accurate quantitative characteristic of intimate processes of neuromuscular transmission in individual synapses. The jitter research test is used for diagnostic myasthenia gravis. The asynchrony of the action potentials of adjacent muscle fibers belonging to the same motor unit makes it possible to measure the transverse dimensions of muscle fibers. If the dimensions of the microelectrodes attached to the dielectrode rod will be so small that the two microelectrodes of the bipolar electrode fit within the size of one muscle fiber, then the dimensions of the muscle fibers can be measured in the same way as we measure the dimensions of motor units by the synchrony and asynchronous electrical activity recorded from these microelectrodes. By asynchrony, we set the depths L1, L2, L3, etc. of the boundaries of the muscle fibers and determine the sizes L2 minus L1, L3 minus L2, etc. of the muscle fibers. Jitter research is also greatly facilitated. If we increase the screw pitch to 1 millimeter, then this electrode connected to a microelectromotor and remote software can be used also in routine electromyography, further significantly reducing its labor intensity. The employment of the proposed electrode in routine tests and single fiber EMG is of crucial importance as the majority of the patients treat of pain and needle puncture. The patient will only feel the pain when inserting the electrode in the muscle. If the needle electrode is inserted in the muscle quickly, the pain will be reduced to the minimum. During the examination, instead of having to move the needle electrode for an hour or more in order to receive a high quality recording, only the dielectric rod inserted in the cannula is moved. In case of the proposed project, while the cannula itself remains motionless in the muscle. As a result, the patient does not experience pains during the examination process. And this moment, sharp decrease of pain and trauma perhaps will allow us to employ DMJ testing with needle electrodes in pediatric patients too. Unfortunately, due to the lack of appropriate production capacities in our country, it is not possible to put this development into the practice in our country. All possible technological difficulties arising during this development and ways of their resolution have been analyzed by us. If any manufacturer will be interested in production of these electrodes, we will help him to easily establish production. Thanks for your attention.